burned off a bunch of chemicals or something, and that was giving it the thrust to the tune of like 13%, and we would see a humongous tail maybe. What is going on?
Everything we understand about comets indicates their tails should point away from the sun. This is a fundamental consequence of physics. However, recent images of our latest interstellar visitor, 3I Atlas, show a feature that has presented a significant puzzle for astronomers: a distinct anti-tail that appears to point toward the sun. In this video, we'll examine the observations of this object, the physics behind its unusual appearance, and what it means for our understanding of interstellar comets. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, flagged a new faint object moving at high velocity. Analysis of its trajectory revealed a hyperbolic path, clear evidence that it was not gravitationally bound to our sun and originated from interstellar space. This made it the third confirmed interstellar object, officially designated 3I Atlas, following Oumuamua and 2I Borisov. Once identified, telescopes across the globe began tracking it. At its closest approach to the sun, it reached a velocity of approximately 151,000 miles per hour, a speed comparable to that of Oumuamua. Its trajectory suggests it may have been traveling through the Milky Way for up to 7 billion years, potentially making it a relic from a time before our own solar system formed. As it moved through the inner solar system, solar heating caused its surface ices to sublimate. Observations confirmed a coma of dust and gas and the formation of a tail. This is expected cometary behavior, but subsequent higher-resolution images revealed something that did not fit the standard model. In late August and September of 2025, images from the Gemini South Telescope and the Hubble Space Telescope revealed an unexpected morphology. The comet presented not one, but two distinct tails. One was a conventional dust tail pointing away from the sun as expected. The other was a bright, linear feature that appeared to point directly toward the sun, which scientists termed an anti-tail. This observation immediately sparked debate. In some comets from our own solar system, a sunward-pointing tail can be a line-of-sight effect. This occurs when Earth passes through the comet's orbital plane, and we view dust left by the comet earlier in its orbit from a perspective that makes it appear to point toward the sun. With 3I Atlas, however, scientists concluded this was a related but distinct phenomenon. The feature was not a jet of material actively defying solar radiation. Instead, the evidence pointed to a projection effect caused by a trail of large, heavy dust particles being left behind the comet along its orbit. From our specific viewing geometry on Earth, this trail of debris appears as a fan, and its edge appears as a distinct line pointing back along the orbit, toward the sun. It is not defying physics, but rather a phenomenon created by a combination of factors: the comet's high speed, a composition that produces unusually large dust, and our specific viewing angle. Understanding this required a coordinated global effort. As the comet passed behind the sun from our viewpoint in October 2025, it was unobservable from Earth. Astronomers utilized spacecraft at Mars, such as the ESA's ExoMars Trace Gas Orbital, to continue tracking it. These observations from a different vantage point in the solar system allowed for triangulation, refining the comet's trajectory with significantly higher accuracy. Now that 3I Atlas has re-emerged into our sky, the investigation has intensified. The James Webb Space Telescope is analyzing its chemical composition, which will provide critical data. Scientists are particularly focused on measuring the ratio of carbon dioxide to water, as an unusually high ratio could indicate that 3I Atlas formed in a very different environment than comets in our own solar system. Supporting evidence comes from spectroscopy via the Very Large Telescope, which has detected elements like cyanide gas and notably atomic nickel vapor in its coma. While not unprecedented, the observed ratios hint at a truly exotic origin. This data is beginning to paint a consistent picture. The leading theory suggests that 3I Atlas is not just an interstellar visitor, but a body chemically evolved by its long journey. Having spent billions of years traveling through interstellar space, its surface has been relentlessly bombarded by high-energy galactic cosmic rays. Cosmic rays are charged particles, accelerated by events like supernovae. Over immense timescales, they alter the chemistry of exposed icy surfaces. When they strike ices containing carbon monoxide, they can drive reactions that convert it into carbon dioxide and produce complex organic residues. According to models, this process would have gradually built up a radiation-processed crust on 3I Atlas. The material we see venting from its surface today, its coma and tails, is likely drawn from this altered layer, not the pristine ice beneath. This could explain both the violent ejection of large dust particles forming the antitail and the unusual chemical signatures being detected.
Instead of studying an untouched piece of an alien world, astronomers are examining how interstellar space itself transforms matter. The comet's surface is effectively a travelogue, recording billions of years of exposure to the galactic environment. As of late November 2025, 3I Atlas is observable in the pre-dawn sky with small telescopes. Its closest approach to the Sun occurred in late October 2025, and it will not pass particularly close to Earth. After its passage through our solar system, it will continue its journey back into the void, never to return. This finding complicates the hope that interstellar comets are pristine samples of other planetary systems. If cosmic rays can significantly alter these bodies, each one may be chemically aged. That realization shifts the scientific focus. Researchers can now treat these objects as records of galactic conditions, using their surface chemistry to learn how long they've traveled and how organic molecules evolve in deep space. This also guides how we will study future visitors. The Vera Rubin Observatory, which is nearing full science operations, is expected to identify many more of these objects, providing more time for analysis. Meanwhile, missions like ESA's Comet Interceptor, already under development for a planned 2029 launch, are designed to rendezvous with a future interstellar object. In short, 3I Atlas transforms our expectations. It demonstrates that interstellar space is not a passive void, but an active chemical environment that shapes everything within it. Each future interstellar visitor will carry a similar message, revealing how the Milky Way itself recycles and reshapes material over cosmic time.